Okay. Okay. Good afternoon, everyone. Let's start where we have left. Let me share my screen again. Okay. So we were here, right? We have calculated the moment distribution factor (DF) of the giant A and the members, different members A, B, and AD. Right now, we have to find out the moment distribution. We can once we know the distribution factor, we can calculate the moment distribution. We can do the moment distribution. So, for the moment distribution, you know how to do moment distribution, but still, I'll show you if you have forgotten. Then just brush up. Okay. So, moment distribution here. Okay. This is your distribution factors. Okay. Here, this one. Okay. These are your distribution factors. Okay. At point A, what was our distribution factor if we see here? You see the distribution factor AB here it is 0.4. So AB 0.4. This is also another one. DF distribution factor. This is a point. Okay. Excellent. This is your A point. This is your B. Or the other way, either way also you can keep the B this side and D this side. So this is your D. Okay. So distribution factors we know. Now once we know the distribution factor, we have this here we had calculated. Fixed and moments we had calculated. AB it is minus 81, AD is 36. So AB minus 81, AD plus 36. Okay, so these are the fixed and moments here. This one you can see the distribution factors are here. Okay, you can cut this then. Distribution factor is mentioned already here. Wait. Okay, so here these are the fixed and moments. Then we have the balancing. We have to do the balancing now. So for the balancing, what you'll do here, you see, these are your minus 81 was for AB, the fixed and moment for, okay, what happened? Okay, this is AD. AD was how much? 36. Okay, now what you're going to do is you have to, this is 18 minus 18 plus 36 into this plus this minus this sorry into this will give you your balance here. So if you do minus 81 plus 36 that will give you your 45. Now that 45 into, okay, I'll just the annotation here. So this will be minus 81 plus 36 equal to 6. 545. So this will be 45. So now this minus this you have got how much? 45. So that 45 into your this 0.5, since we have here, this one 45. So 45 into, if we do now 0.4, we will get this value 18. Hmm. Okay, this is also here if you see. Here it is minus. Okay, fine. Minus 45 into this one. That means how much is this here? Minus, we will have here how much? This 45 into 0.4, if you do, that will be how much? 18. Minus 18. Yeah. Balance. Then we have here, if you do same thing, this one minus 81 plus 36, 45 you are going to get. Now this into this 0.6 equal to how much? We will get, this is 180. Okay, sorry, 27. 27. This into this, because whatever this minus this, we got this 45 into now 0.6, so we'll give 27. So this is 27. Okay, now, and here we don't need the balance. We are not going to, with balance we are not going to consider the signs. Okay, so this will remain positive only here. Oh, it is not going, whatever. So now what you're going to do now, if you see this 27 plus 36 here, 27 plus 36 will give you your 63. Then we have here minus 81 plus 18. This is plus, okay. This one is a plus 18. That means how much here? Again, you'll get here minus 81 plus 18. That will give you minus 63. So when you have this, now this is balanced because the signs are opposite signs. So when the moment at the end, suppose these are the final moments here, you will see this are your final moments fi and your final mo and ts moments. Now since this sign is opposite here, this now it is balanced already, 6.3, sorry, 63, and the minus 63 here. So final moments you have got this to be this much. That means our pending moment at the end supports is here, this one 63. Okay, so we have calculated our, we have done the moment distribution now. So now again, if I remove the annotations, this is going to go. So if this goes here, what will happen? Let me check. uh, Okay, it's gone now. So once we have, so bending moment at the center of long span AB is equal to how much? Now we'll find out after doing the n moments we have calculated, right? Once we have calculated the n moments, what will happen? Once we have calculated the n moments here, bending moment at the, now we'll calculate the bending moments at the center of the long span and the center of the short wall. Okay, the long wall was AB and the short wall was your AB, this one AD or BC, you can say. So bending moment at the support, we got it to be how much? 63 kilonewton meter. 63 kilonewton meter. 63 kilonewton meter. Now at the center of long span AB, what is our bending moment WL square by 8 minus our moment which we have got at point A, the support A, WL square by 8 minus your support. You will get a bending moment at the center from all the total moment WL square by 8 minus your fixed end moment here MA. That will give you your the support here. You got this much. So now your uh, center at the bending moment of the longer span at center is how much? 58.5 kilonewton meter. Now bending moment at the center of short wall, if you do this, so short wall again you'll see WL square. Now here the difference is what? This MA and this MB the same here, 63 63, but you see here this at the center of longer span, when you are doing in the longer span, you have your L to be 6 meter, and at the short wall when you do this is how much? This is your 4 meter. Okay, so this becomes your 9 kilonewton meter. Your the bending moment at the center of the long span is 58.5 kilonewton meter. The bending moment at the center of the short wall is 9 kilonewton meter, which is nothing but this is your figure. What you have on the supports, this is your point A, this is B, this is C here, and this is D. So you have your supports here. Support moments are given to you here. You can draw here 63 plus it was 63, 63, and then at the center of the long, this was your longer span. AB is a longer span. So along the longer span, you have how much? 58.5 kilonewton meter is your moment, the center span moment. When the moment at the center, then we have on the short span, you have how much? 9 kilonewton. It is okay. 9 kilonewton meter. Actually, this diagram is little wrong. Okay, don't follow this. I'm showing you. I have to take the annotation here again. Let me draw. This is a short wall. Okay, short wall. This is a long wall. Hmm. So we have this. Now, what we are going to do here at the, this is point A, this is B, this is C, this is D. At point A, at the supports we have 63 kilonewton, all minus. At supports it is 63. At E, 1 minute. Oh, 63. Right. AD. Okay. So if I draw again here. Okay, I'll take the pencil only. This one is a support moment. Okay. So now you see here it is 60, here also. Okay, this one. This is 63. Then we have here, okay. So here it is 63. Here it is 63. This is minus, minus. Here also it is 63, 63. So all the supports here are 63. Okay. Now here also it is minus. Okay. So and what was the center at the longest one? This is the longest span, 6 meter. This is the 4 meter. Now here it is how much? Here it will be this one. 58.5. Here also it is 58.5. Here it is 9. Here also it is 9. Okay. So this is your moment diagram. Okay. We have got the support moment 63, 63 minus, and wait. Okay, I can write here a different color. This will be your A. This is B. Then you have C and D this side. This is C, and here you will have your D. So these are the moments here, the support 63, 63, and at the center of the longer span it is 58 here you see, and at the center of the short wall it is 9. So you see here 9, you can see. Okay, so this is the correct one. This is wrong. This one is wrong. Do not follow this, okay? Done. Okay. Now, if we see, we have calculated the bending moment at the center, long span, short span. Now we'll find out the tension in the long span, longer wall, and tension around the shorter wall. Okay, because if I show you, yeah, on this longer wall there are this water. There is water here, and this has what the pressures are falling on the inner wall of the 6 meter longer span wall and the shorter span also here. Okay, so what will happen now? When you have this, there will be tension in the long wall here due to this load. There will be due to the pressure from the water. Here will be tension. This there will be also tension in this long wall as well as in the short wall also. So we are going to find out the direct tension along the longer wall and along the shorter wall. So the direct tension in the long wall is how much? P, that is WL by 2 actually. So WL by 2 along long wall. But what we are doing is why PW into B? W we know already it is 27. The load which is falling, the pressure is 27. This one, the pressure which is acting above, because we are finding out we are trying to design it in a continuous frame. So the this one 27 is your load. WL by 2. So why the B I have written along the longer one. So since it is along the longer wall, WL by 2, but I have written WB by 2. Why? Because this is a longer wall, but we are going to consider this shorter wall span. Why? Because we are considering now the longer one, and when we're finding out the tension here in the long wall, 1 minute. Okay, sorry. Then we have what? Yeah, we have considered this longer wall, but why we are taking this shorter wall dimension with why? Whenever we because we are finding out the tension here in the longer wall. So when we are finding out the tension in this longer wall, this is due to the factors on the shorter wall. Okay, because when this pressure comes here, this is gonna be affected here, this shorter span. So therefore we always take to be this shorter span. Okay, here this one WB by 2, and same case for when you're finding out the direct tension in the short wall, then we take the opposite one. This was your shorter wall, which is 4, but we are considering the longer one because due to this pressures here, the tension which should be there due to this, okay, that will be here on the tension will be here on this wall, longer wall, due to this pressure. So that is why it is the WL by 2, that is 27 into 6 by 2, that is 81 kilonewton. So the direct tensions also we have calculated for the longer wall and for the shorter wall. Now once we have calculated this tensions and the longer wall and the shorter walls, we can find out the thickness, or I can see the depth, okay, of the walls. So we had derived some, there is a derived formula for that, which is M is equal to Q into, this is into, this is M into, Q, sorry, M is equal to Q into BD square. Now Q we had calculated before, this one previously we had calculated the value of Q, that is the moment of resistance factor. This is required to us, that's why we had calculated this constants, and to calculate this we had to calculate the lever arm coefficient, neutral axis coefficient. So Q, we need that moment of resistance factor. So now, when you have the moment of resistance factor, you can use here the moment of resistance factor. You know the moment. At the how much was your moment? 63, 63. So once you put these values here, the moment value, Q value, B is per meter. We are considering it to be per meter length. So 1000. So D we can calculate from here. The depth, that is 187.8 mm. Now let us consider the depth to be. We can consider it to be greater than this value. This is the minimum requirement. So you can consider the depth to be the 200 or 250, whatever you want. But for this particular question, we have considered it to be 250 mm. And let us consider the effective cover to be 50 mm here. So it becomes how much? Your depth becomes 300 mm. Okay. So that means now what is your thickness? That is 300 mm. Okay. One second, please. Okay, so this is the depth which we have got. Sorry, the thickness, we can say the thickness or the depth, whatever. So that is just 300 mm. Okay, now once we have known all the depth, etc., so we can design the longer wall and the shorter walls. Okay, we have known now the thickness. So to design now the longer wall, what you have to do is, we know the moment here m, kilonewton meter. Then we know the tension is 54 kilonewton. This one. Now the modified moment is how much? This moment m minus, there will be a small amount of movement due to the tension of the, due to the tension. Okay, so that is T into X. Okay, let me see if there is some drawing. Oh, so I have to show you. I have to show some annotation again. Sorry. So this is the tank. Okay, here you will see this is the thickness which we have got 300 mm here. This is 300. Mm, Then we have the center here. We have the center here. Then we have another one line. This is your tension. Okay. This is your tensions here. This distance from the center to the reinforcements is your x distance. Suppose I'll show you. Here there are reinforcements. Okay. A reinforcement. Hmm. So this distance is, we let us consider this distance to be x. This distance to be x distance. Now the moment due to now this is this moment. Okay, the total moment here at the support is 63, and there will be some amount of moment due to this tension here. Suppose this is the tension, and at a distance of x, this is your rods here placed here. So this, there will be a moment here due to this tension. So that is T into, this is your T into x. Okay, attentions are in this way. So it is T into X. Hello? What I say? Okay. So this is the modified moment at the support here, 57.6 so to 7.6 kilonewton meter. Now the a net moment, this is a net moment. Okay, the modified moment is 63 minus Tx, and the net moment will be now 63 minus your, this is tension was 54 into your x. This x we have considered it to be 100 mm. Okay, this distance 100 mm, let us estimate to be 100 mm. So this is comes out to be this much in meter, 57.6 square newton meter. Now the area of steel for this moment is how much, given by m by sigma st into j into d, which you had calculated in the previous the constants when you are calculating sigma st into j into d. So sigma st is 130, j is this much, d is this much. Now ast of tension, area of the tension is area for tension, this was area for moment, area of steel for moment, this is area of steel for tension. So that is t by sigma st, this much it is, it comes out to be this much. Your area of steel for tension is this much. Now total area of steel is how much? Area of steel for moment and area of steel for tension is this much. So we will provide 20 mm. Let us provide 20 bars at 120 center to center. So the area of steel required will be pi d square by 4 pi d square by this and this spacing into 1000. That will give our area of the steel required. Okay. Okay. This is still here. This is your area of the steels required at the supports. Okay, we were doing at the design of long wall at the support, this all were at the support. Okay, at the support we were doing, so this is the support. Now we'll do for the at the center, but I have a meeting right now, so I think I'll will continue in the next class. Okay, and please give me your attendance in the WhatsApp group there, whoever is present. Okay. Let me check. Okay, na? Okay, Bimal Shimti. Okay, okay, okay. So I have a meeting now. I think we have already. Maybe the meeting will. This one. The meeting will get over in a few minutes also. After 5 or 6, 7, 8 minutes. So, today we'll stop here now and give you attendance. Give the attendance in the WhatsApp group. Okay. So thank you. I'm okay. I am ending the meeting.